Now let's take a look at the inner sphere mechanisms. In inner sphere mechanism, bonds are broken and made. I would like you to recall the the outer sphere mechanism. In outer sphere mechanism, no bonds are made and no bonds are broken, but here bonds are made and bonds are broken. And in this case, in inner sphere mechanism, there will be a bridging ligand and the electron transfer takes place through bridging. And now I'm going to take examples and then explain you in detail how this really happens. Here we have a classic example. What's happening here? First, let us take a look at this. What's happening here? Here the cobalt is in what oxidation state? +3 oxidation state, and chromium is in +2 oxidation state. And here, take a look at this. Here cobalt is in +2 oxidation state and chromium is in +3 oxidation state. So what's happening is an electron is transferred from chromium to cobalt, and cobalt 3 becomes cobalt 2 and chromium 2 becomes chromium 3. So basically there is an electron transfer happening from chromium to cobalt. So how is it happening? This is a redox reaction because there is an electron transfer from one metal to another metal, and but how is it happening in this case? And we have seen in outer sphere mechanism the oxidant and reductant come close and form a precursor complex, and then they form an activated complex. The electron transfer takes place and the dissociation of the activated complex finally happens. But in this case, what happens is a bridge will be established between the where is the cursor? Not the precursor, it's cursor. Okay, a bridge has been established between cobalt and chromium, and a dinuclear complex has been formed. The first step is one of the ligands from the cobalt complex replaces one of the ligands on chromium and forms a bridge. What's happening? Yeah, forms a bridge like this. Basically, it has to be chloride, which is it has to be chloride, the one which forms a bridge, because ammonia doesn't have another pair of electrons to coordinate with the chromium. Okay, so chloride replaces one of the water molecules in the chromium complex and establishes a connection. It forms a bond. So the bonds are made, and now what happens is that an electron transfer takes place from chromium to cobalt through the chloride bridge, and chromium becomes +3 and cobalt becomes +2. Once the electron transfer takes place, a bond will be broken. That is, the metal chloride bond is broken and the chloride goes with the chromium. You can see that the chloride is going with the chromium. But why is it going with the chromium? It's an interesting thing. You can see that actually cobalt in this complex, is very inert, and chromium here is labile. Since chromium is in +2 oxidation state, it's labile, and cobalt is in +3 oxidation state, that's inert. So that's the reason why a ligand from this, that is a chloride, can easily replace a water molecule from this and forms a bond. So that is a bond. But once the electron transfer takes place, chromium becomes 3 and cobalt becomes 2. That means that actually chromium becomes inert and cobalt becomes labile. So now which bond has to be broken in this? It's the same, this is the same complex anyway. So now you have here chromium 3 and cobalt 2. Now breaking of this bond versus this bond. Since chromium is in +3 oxidation state, it's inert, and since cobalt is in +2 oxidation state, it is labile. So this bond will be broken and the chloride goes with the chromium. Okay, once again, since cobalt is in +2 oxidation state, this bond is labile, and since chromium is in +3 oxidation state, this bond is inert. So therefore breaking of this bond is preferred, and hence the chloride goes along with the chromium and gives this complex. Yeah, this table shows how important the formation of a bridge is in inner sphere complexes. Take a look at the rate constants for the reduction of cobalt 3 by chromium 2. And take a look at the ligands. Here you have a CO NH3 taken 5 times X. So X can be NH3 or H2O or anything, any of these things. And here chromium is in +2 oxidation state, and cobalt is in +3 oxidation state. Basically here an electron transfer takes place from chromium to cobalt. So that is the reaction. So in this reaction, when X is NH3, the reaction is really slow, and when it is replaced, when X is H2O, it is okay, but when it is like OH minus or any other halides or the azide, when the reaction rates are really high. You can see that actually this is 10 to the power of 6. That's a great magnitude compared to the 10 to the power of -5 in case of ammonia. So why is it like that? Because the formation of a bridge is integral part of the electron transfer in inner sphere mechanisms. That means the cobalt and chromium X. This bridge is very important for an electron transfer to occur. If any one of the ligands, if none of the ligands on cobalt are unable to form a bridge, then the bridge formation cannot happen, and the electron transfer has to occur through outer sphere mechanism, but not through inner sphere mechanism. So when you have X equals to NH3, then the complex is CONH3 taken 6 times plus, so that is nothing but the hexamine cobalt 3. So this here in this complex you have all 6 ligands NH3, and NH3 has only one lone pair of electrons which has already been donated to the cobalt, and it has no additional pair of electrons for it to form a bridge with the chromium. So therefore a bridge formation is not possible when all the ligands are ammonia. But whereas in other cases like OH minus, F minus, and those ligands have additional pairs of electrons basically, and they can easily donate additional pair of electrons to chromium and form a bridge, and can form a dinuclear complex like this. That's the reason. Then of course the electron transfer will happen very easily. So that's the main reason why at least one ligand on the oxidant must have additional lone pair of electrons for an inner sphere mechanism to happen. So that is the most important thing. And yeah, in case of water, X is water, you have 0.5. Probably water is not a good bridging ligand, therefore it is actually not able to I mean the rate constant is not that great, but still is much better than ammonia. And I quite often ask my students one question: why do you need to have a bridging ligand? I mean a ligand which is capable of bridging on the oxidant. Why not on the reductant? Why do you need to have at least one ligand which is capable of bridging on the oxidant? Why not on this? Why can't this one establish a connection? I mean this one of these ligands can replace one of the ammonia molecules and form a bridge for an electron transfer to occur. But I would like the viewers to answer to this question in the comments. The students should also send me through WhatsApp or email the answer for this one. Okay, that is one evidence to show that the bridge formation is necessary in case of inert sphere mechanisms. And there is another evidence which shows that actually when these reactions, for example, when this reaction is conducted in presence of isotopically labeled chloride ions, the free chloride ions, none of the isotopically labeled free chloride ions has entered the chromium complex. It's always the chloride which is there on the cobalt, which is there on the cobalt, entered the chromium complex, but not the free chloride ion. That shows that actually this chloride forms a bridge and then transfer to the chromium, but not the free. I mean, it doesn't break and become a free chloride ion and go to chromium. That's not the one which is happening. If that is the case, then the free chloride should enter the chromium. That is another evidence that the ligand transfer is taking place through the bridge. It is not true that the bridging ligand always goes with the other metal. And here you have two examples. In the first case, the bridging ligand, that's a chloride, goes with the other metal. That means that actually originally it was there with cobalt, and now at the end of the reaction it goes with chloride. But in this case, if we take a look at that, the iron complex has 6 cyanide ligands, and at the end of the reaction also you have 6 ligands, and cobalt is having, to begin with, 5 ligands, and then at the end of the reaction also it has only 5. So what is happening? Why the ligand is not transferred in the second case? If you take a look at the intermediates, that is the dinuclear complexes in both cases, then you will come to know. And in this case, for example, after the electron transfer, the chromium is +3 and cobalt is +2. Cobalt 2 is labile and chromium 3 is inert. So now this cobalt chloride bond is labile, so therefore it cleaves here, and this is inert, so it doesn't cleave. So therefore the chloride goes with chromium. I have already described in the previous slide. I am just trying to recall this again, and yeah, that is how it happens. But let us take a look at this one. The cyanide cannot form a bridge through carbon. That means, what I mean is, the carbon cannot be connected to both iron and cobalt, and the cyanide can form a bridge like this. That means carbon originally connected to with the iron will remain like that, and the nitrogen now is connected to cobalt. So cyanide can form a bridge only like this. Okay, once the bridge is formed, you know that actually an electron transfer takes place from cobalt to iron, and cobalt becomes 3 and iron becomes 2. So both are actually D6. And now take a look at the metals. One is N bound, I mean the cyanide is connected to the cobalt through nitrogen. In another case, cyanide is connected to the metal through the carbon. So both are D6 systems. Now here, N-bound cyanide stabilizing the D6, or C-bound cyanide stabilizing the D6. So which one will be stronger? Obviously, C-bound cyanide stabilizing the D6, that is actually iron 2, is certainly more favorable than N-bound cyanide stabilizing the D6, that is cobalt. So therefore what happens here is this bond breaks, because this gives a complex, the cleavage of this bond gives a complex where a D6 system is stabilized by a C-bound cyanide. But if this bond breaks, for example, then you will end up with a complex where the cyanide is connected to the metal, that is cobalt, through nitrogen, which is not stable. So the preference will be the I mean, here you will have a 3 minus. Yeah, the preference, I mean, this bond is preferentially cleaved to give this complex, that is basically this complex. Yeah, and there, let us see if the bridging ligand contains more than one donor atom capable of bridging. So what happens? For example, you have SCN minus. SCN minus can coordinate to the metals through nitrogen as well as through sulfur. And you can see that, for example, you have a metal connected to SCN like this, and if this metal, I mean this complex, is undergoing a redox reaction with another metal complex, then SCN can form a bridge either this way, or it can also form a bridge this way. When SCN minus, that is thiocyanate ligand, forms a bridge this way, it is called adjacent attack. This is the adjacent attack. That means that actually the same donor atom is connected to both metals, and if SCN forms a bridge like this, that's a thiocyanate ligand forms a bridge like this, and it is called remote attack. In case of nitro, this is the only way the nitro can form the bridge, because nitrogen doesn't have additional pair of electrons, so the adjacent attack is not possible in nitro case. But when the nitro forms a bridge, it's always going to be like a remote attack, and it gives rise to isomers, because it gives this complex, and this complex can isomerize to give you this complex. And I hope you understand what is an adjacent attack and what is a remote attack.